Hi, everybody. Welcome to exam week. Always an exciting week. So today is all about getting ready for this exam. So I have, the various handouts. We can look through old quizzes, whatever you want to, work on today is good. So please leave your requests, suggestions, questions in the chat or on Discord. I have one to look at here from the end of last week. So I'll get started on that, and then as you have things you want to talk about, just leave them, and we will just go in the order that we see them. So the first one is about the latest handout on solutions and mixtures. So let's take a look there. Yes, I will definitely go over intermolecular forces. That's fine. So there's a question about number 31 here from this latest handout. So let's just go through it. What is the molarity of a solution with 9 grams of potassium carbonate and enough water to make 67 milliliters of solution? So in this case, we always want to start from the definitions. So molarity, because we can that's either the way we're going to solve it, or it's a conversion a factor. We're going to use it as a conversion factor. Sorry. So molarity is moles per liters. So that means we need to know the solute amount in moles and the solution amount in liters. So we have the 9 grams of potassium carbonate is given, and then 67 milliliters of solution. So 67 milliliters, we can divide by 1,000 to get liters. So we got that. But this top part, the moles of potassium carbonate, that's going to take a little bit more of a conversion. So that we're going to take that 9 grams of potassium carbonate, and we're going to go from grams of potassium carbonate to moles. And the question was about calculating these moles. So we need to get 2 potassiums, which are about 40 each. And so that's about 80. And then carbon is 12, so that's like 92. And then 3 oxygens at 16 each. That would come out to about 130. Yeah, 130. So if you're getting more than that, maybe you're counting too many carbons or just like got the wrong number in there somewhere. But it should be about 130 grams per mole. So you would divide that and get 0.069 moles of K2CO3. So that number becomes our numerator over here. And so we get about 1.03, whatever, about 1 molar. All right, while we're here, let's look at number 36 also, since that's a request here. So here we've got a dilution. What is the final molarity of a solution prepared by diluting 20 milliliters of a 4 molar solution to 10 liters? So remember with dilution calculations, as long as you've got the same units on both sides of the dilution before and after, it doesn't really matter what the compound is or what the units are. In this case, we don't have that because we've got 20 milliliters of our stock solution and then 10 liters of our final solution. So if we just plug that directly into the equation with 20 and 10, we're going to get the wrong answer because one of them's in milliliters and the other one's in liters. So we need to convert one of them. It doesn't matter which one. We can convert milliliters to liters, or we can convert liters to milliliters, but the beginning volume and the ending volume have to be the same unit. as does the beginning concentration and the ending concentration. So let's convert 20 milliliters to liters. So that would be 0.0200 liters. And now we can plug that in. The initial concentration is 4 molar, and the initial volume is 0.02 liters. And then we want to find the final concentration that is in 10 liters, as after we've diluted it to 10 liters. So we're going to multiply 4 by 0.02 and then divide by 10. And we get that final concentration is 0.008 molar. Or if we want to, as we get into these later and later, or these smaller and smaller numbers, it might be more easier to read if we think about it as 8.00 times 10 to the minus 3 molar. With big numbers and small numbers, we often like to express them in scientific notation so that we can be really careful about how much precision we're reporting. That's not something you'll have to necessarily do on the exam unless it's explicitly asked for. Express your number in scientific notation. But if you'd rather leave it like this, that's fine. Okay, so now we've got requests for looking at intermolecular forces and VSEPR, which is molecular shapes. So let's go back and review some of that stuff. We'll go back to the intermolecular forces first, just because that was asked first. All right, so here's this handout here is kind of your general review for these forces. In general, we're going to have polar and non-polar forces. So the polar ones are going to be generally stronger, the non-polar ones weaker. The non-polar forces are the ones that have the dispersion forces. So that's where you don't have any kind of polarity. You don't have really a separation of charge. You just have this induced dipole, which makes non-polar molecules have some interaction, but it's weak compared to the polar interactions. As the molecules get bigger, those forces can get stronger and stronger. So that in very large molecules, large nonpolar molecules can have significant attractive forces, but really small ones usually don't, and that's why things like methane or ethane are gases at room temperature. That would be CH4 or C2H6. So then as we move into the polar forces, there's really two important ones that we're going to talk about, that we talked about. The dipole forces, where you have polar molecules that have a positive and a negative side, and then they attract each other. Positive sides attract negative sides. But with the dipole forces, when they're most important is in molecules that are polar, but that don't have OH and NH bonds. So things like CO, CF, CCl to some extent, things like that, where you don't have SO, that sort of thing, where you don't have HO or HN. Because when you have HO or HN, you now have the capacity for hydrogen bonding, which is the strongest type of intermolecular forces. Well, okay, the bottom ones here are a little stronger, but we sometimes don't think of those as intermolecular forces exactly. And so those are the things that like hold the base pairs together in DNA. So what you want to be able to do with this is this sort of thing. What type of forces does this molecule have? And then can we judge the strength of those forces by the polarity? So that's the idea there. And so while we're in this handout, let's look at number 53 by request. Yeah, so arrange the 4 compounds from lowest to highest boiling points. And let's take a look at the structures and see. So we've got methane CH4. This will also help us review VSEPR as well, because we may want to look at some of the structures here. When we want to look at structures is when we're not sure if it might be polar or not based on the atoms that are there. So yeah, so just as the questions just came in, how to figure out if it has polar bonds. So first, we're going to look at the atoms that make the bonds in the Lewis structure and see if there's a difference in electronegativity there. So CH4, the Lewis structure might look like that. And so we want to know, yeah, exactly, if it's greater than 0.4. We want to know, is the difference in electronegativity between C and H greater than 0.4? And one thing that I think it's worth just remembering is that C and H bonds are not polar. Their electronegativity difference is actually is at 0.4, but they're considered non-polar bonds. And those come up so often and they're so common that it's good to just remember that those are non-polar bonds. In general, even if you don't know those numbers, you can still get it from the periodic table, as long as you remember that fluorine is the most electronegative element, and there's relatively big drop downs as you go to the left and as you go down. So like, for example, fluorine has an electronegativity of 4, oxygen's 3.5, nitrogen's 3, carbon's 2.5. You don't need to remember those numbers, but just recognizing that as you move to the left, the electronegativity is dropping a lot. So any bond between something over here and something over here is generally going to be polar. So a CN bond, a CO bond, a CF bond, a PCl bond, an NF bond, any of those kinds of things. As you go this way, it gets a little trickier. So like, is a CBr bond polar? That's not something that you can really get from the periodic table. That's not something I would ask on an exam. But is a CO or a CF bond polar? Yes, you should see that that is polar. The weird one, which again is worth just remembering because H is way over there, is that CH bond is also non-polar. So back to the question here, we can say that methane is made from all non-polar bonds. So there's no way, regardless of what shape it might be, there's no way it's going to be polar because all the bonds are non-polar. You have to have those polar bonds to start with for the whole thing to be polar. But just for review, if we wanted to know what the molecular shape of methane is, we would go, okay, methane has a central carbon and then 4 groups around it. So those are going to arrange themselves in a tetrahedral geometry. And if we go back to that handout, which I will open up. And we go back to this table, we can see that we've got 4 groups and therefore tetrahedral. And I told a couple of people asked, I will put this chart on the exam. You don't have to memorize this, but you do have to know how to use it. All right, so back to this. So that would be tetrahedral. Then we've got octane. Now octane's a big molecule. We can't use that chart for octane really unless we're looking at every individual carbon differently. But we do see here that it's C8H18, so that means it's all carbon and hydrogen, so it must also be nonpolar. All right, so now moving over here, let's skip ethanol for a second and go to water. We know water. We've talked about water a lot. We know that's the structure. We know it's bent. We know it's polar, and we know it exhibits hydrogen bonding. So that leaves ethanol. Ethanol, we've got C2H5OH. So this is going to be kind of the tricky one here. We can get a Lewis structure here. Remember that these organic structures with lots of carbon and hydrogen, are often expressed in such a way that helps hint at how they're connected. So the fact that it's C2H5OH rather than C2H6O is telling us that it's OH, that the O and the H are connected, and that they shouldn't kind of be stuck in somewhere else. So the O shouldn't go in between the 2 carbons, for example. If we just had a molecular formula, we wouldn't have that clue, and there would be lots of different ways of distributing those atoms. Well, in this case, not a lot, but I have 2 different ways of distributing those atoms, and we could have 2 different structures. But in this case, it's very clear that it's meant to be OH, and to complete that Lewis structure, we've got a couple lone pairs. All right, And then question as before, do we need to know something about the shapes of this molecule to answer this question, to figure out things about their intermolecular forces? And in this case, we do not, because we can already see right here, it's got this OH, and then it's also got this big nonpolar part. And then we've got water over here. So that's really enough to talk through this question. And I'm just going to tell you, this is not an easy question. This is not an exam level question. This is a higher than exam level question. But that's okay. Let's talk about it and see what we can get. So lowest to highest boiling point. Well, hopefully, and this would be an exam level question, you should be able to see that the lowest boiling point for these, between all these four molecules, is methane. It's nonpolar and it's very, very small. Octane, C8H18, is also nonpolar, but it's much, much bigger. And so this is going to be something that is going to definitely have a higher boiling point than methane. Not sure about these other ones yet, but definitely higher than methane. So all of these compounds would have a higher boiling point than methane. So if I wanted to ask this question in a test appropriate way, I might ask, which of the four compounds has the lowest boiling point? Because that should be fairly clear, that methane is the lowest boiling point. The ethanol and water both have this ability to hydrogen bond, so we expect that those to have higher boiling points anyway. So methane's for sure the lowest. Now, as we go up higher, this is where it really gets tricky, because I would guess that if I asked you to rank these, that you would mostly get it wrong, I would say. I think most people would mostly get this wrong. And the reason is that it's hard to judge the strength of different forces when there are different types of bonds present. So for example, octane is nonpolar, but it's also very big. And if we actually look up these boiling points, octane has a higher boiling point than water. In fact, octane has the highest boiling point of this whole group. This is actually the highest boiling. And that's not something that you could necessarily grab from the structure because it's nonpolar. You might expect that it's actually has a lower boiling point. So don't worry if you didn't get that. And then between these two, same thing. Ethanol is bigger, but water has more possibilities for hydrogen bonding. So water actually ends up having a higher boiling point. So the real ranking from lowest to highest is methane is the lowest, then ethanol, and then water, and then octane. And that's not obvious. And I forgot when we went through this before that I put this on here as a not obvious, unclear example to go through in class, and we didn't actually go through it. So thank you for asking about it. So for your perspective, ranking boiling points based on intermolecular forces, I would expect you to be able to say, okay, these small nonpolar things are the lowest boiling point, weakest forces. Things with hydrogen bonding, strongest forces. I wouldn't expect you to put them in that careful of an order as this question asks. All right, let's see. I want to check Discord here, see if I've got other questions coming in. All right, let's jump back to, we didn't quite really go through the whole Vesper thing, so let's talk a little bit about that. All right, so here, this is really all you need to know, and again, I'm going to give you this table. But you look at a Lewis structure, you count the number of groups, and when we say groups around the central atom, we mean bonded atoms and lone pairs, 2 electrons. Double bonds, triple bonds still just count as one group. So the number of things around the center, because remember the theory behind this is that things are trying to space out as far as possible. So it doesn't matter if something's a double or a triple bond, it still wants to be as far away from the other thing as possible. So you use that to determine the electron geometry, and then based on the number of lone pairs, that gives you the molecular shape. So doing all of this really the skill that's required first is getting the correct Lewis structure. So let's take a look at some of these. Let's just look, since it's right here, let's look at H2CO. So we got to get the right Lewis structure for H2CO. So we can count up the electrons. We've got one from each, the valence electrons, we've got one from each hydrogen, 4 from the carbon, that's 6, and then 6 from oxygen is 12. So that gives us 12 electrons to work with. We know the hydrogens can't go in the middle, so we're going to assume the carbon kind of goes in the middle and then everything comes off of that. Maybe like this. Remember, when you're first getting the Lewis structure, you don't have to worry about bond angles because we don't know what they are necessarily until we have the lone pairs in the right place. All right, so that gives us 6 more electrons. And so they're going to go here and here. And then we've got one more pair. And we notice that if we put it here, the carbon's not going to have enough electrons. And if we put it here, the oxygen's not going to have enough electrons. So that's our clue that those have to be shared in a double bond. All right, so there's our Lewis structure for H2CO. So now we can count the number of groups around the central atom. There's no lone pairs on the central atom, but we have 1, 2, 3 groups. So coming back up to our table, that tells us that we're going to have trigonal planar geometry. And if we wanted to draw that, we just kind of need to space things out a little bit more so that we have those nice 120-degree bond angles. Like that. Oh, I forgot my lone pairs. All right, and while we're looking at this molecule, let's think about the polarity also. So in this case, we don't have any OH bonds, but we do have a CO bond, which is polar. And we know the CH bonds are nonpolar, so we can kind of ignore them. So when we're thinking about the polarity here, we really only have to look at the C and the O and recognize that, looking at the periodic table again, C is here, O is here. So that's going to be a pretty big difference in electronegativity. So we're going to have partial positive on carbon, partial negative on oxygen. That gives us a nice place to cut the molecule where it has a positive side and a negative side, and that tells us that it is polar. So this compound we would expect to have dipole-dipole forces as the strongest forces. It would also have dispersion forces because everything has dispersion forces, but this one would have predominantly dipole-dipole interactions would be the strongest types of forces present there. All right, how is that for the questions so far? Anything more that you want to go over those, or if you have other things that you want to talk about? No, everybody's good? Moles. All right, let's do moles. So we did that a little bit with that molarity question earlier. But let's jump back to where we really started talking about it. And so actually, before we go to this, I want to look at Blackboard and just make sure that we have enough, not enough, that you are looking at these objectives also when you are, when you're studying, so that you're not studying things that aren't a great use of your time in this case. It's always nice to learn new things, but obviously you want to study the things that are most relevant right now. So let me pull Blackboard up here, if I can. Great, there it is. And so these learning objectives here are like, so when we go to look at moles, we did a lot of stuff with moles, but let's focus on the things that we have to actually do with moles. So we want to be able to calculate the formula weight of a chemical compound, or the molar mass, where we add up the masses to calculate the overall weight. We want to know the number of moles in a given mass of a substance and the number of grams in a given number of moles. And let's just check out, just make sure that's... Oh yeah, and then there's one more here that we talked about, calculating the molar ratios, which was just the mole to mole ratios. So notice that some of the stuff that we went through in the handout here would not fit in those categories. So for example, doing calculations with Avogadro's number is not something that you can expect to see on the exam. We'll focus on the mass and the mass to mole conversions. So things like, how many moles of something do you have in a certain number of grams? So let's take a look at one of these here. How many moles of carbon atoms do you have in a 21.235 gram sample of ethanol? So ethanol is CH3CH2OH, or C2H6O. So the molar mass, to get that, we're going to count up 2 times 12.01 for carbon. And then we're going to add that to the 6 hydrogens. And we're going to add that to oxygen, which is 16, and we get 46.08 grams per mole. How many moles of carbon atoms? So to figure that out, we first need to know how many moles of ethanol molecules we have. Then we can talk about moles of just the atoms with another conversion. So we're going to go 21.235 grams of ethanol. And we're going to convert grams of ethanol to moles of ethanol using the molar mass. So that's 46.08 and 1 mole. And then that gives us 0.461, and then we have to remember that's moles of ethanol. So that hasn't answered the question yet, but that's given us moles of ethanol. So then we would need to recognize that every molecule of ethanol, or every mole of ethanol, has 2 atoms of carbon, or 2 moles of carbon. So the answer is going to be double this. We want to know how many moles of carbon atoms. We know we take the number of moles of the whole molecule, and then we double it, so that will be 0.922 moles for just carbon, because there's 2 carbons in every molecule. So that's really the most difficult type of mole question you'll need to be able to do, but you'll also need to be able to calculate molarity and deal with molarity from a later chapter. So the last few chapters that we worked on really all work together. Oh, and I missed a question earlier. I just noticed now. Variables held constant for pressure, temperature. So talking about gases, let's go back to that table here. So when we deal with gases, we can think about all those different variables: pressure, temperature, number of moles, and volume. And often when we want to kind of zero in on a particular thing that's happened and explaining a phenomenon, we really need to focus on just 2 of the things changing. One of them changing, which causes the other one to change. And that means the other 2 have to be held constant. So if we are, let's say, taking this one over here, lungs expand as they fill with air. Well, expansion is going to be a change in volume. And filling with air means they are changing the amount of air in there. So that would be number of moles. And so that means that pressure and temperature are staying constant. So you got four things: pressure, temperature, number of moles or amount of gas, and volume. And you're always going to have two of them changing and two of them staying the same. You can actually have more than two changing, but whatever isn't changing is staying the same. So if you remember, there's four. So rather than saying et cetera, just say pressure, temp, moles, and volume. And then whatever two are changing, the other two are staying the same. So jumping back down here, a can of air gets cold as it's used to blow dust off your keyboard. So as it is used would mean, I guess, I guess there's a couple ways to interpret that. That's not a super well worded question. Sorry about that. It's really we could think of it as clearly it's lowering the temperature, right? It's getting cold. That's the important thing. The temperature is lowering. But we could think of what's causing that lowering in temperature as a reduction in pressure as it exits the pressurized can, or an expansion, an increase in volume as it exits the can. Those are all things that are happening. So there isn't really a correct answer there as to what is absolutely being held constant, because we can also think of it as a change in N, because the moles of gas are going down as it leaves the can. So too many possible things changing in that one. Not a good example. Sorry. All right. Other question was the difference between osmosis, dialysis, and diffusion. Yeah, let's pull that one up. Those are a little bit confusing terms because they're also used in, whoops, going the wrong way. They're also used in our life, and sometimes mean different things. So when we think of dialysis, we think of like a machine that is cleaning toxins out of your blood when your kidneys aren't working properly. And that is actually using the concept of dialysis, but it's a little bit different. Osmosis is another term that gets misused. It's just like things changing or moving or something like that in general, when it really has a specific definition. So let's look at the specific definition. So first of all, diffusion is the most general overall term. Diffusion simply means things going from areas of higher concentration to lower concentration. So if you have something that smells in a room and you put it in the corner of the room, eventually it will diffuse and go throughout the rest of the room, because the higher concentration vapor doesn't stay there. It eventually mixes with everything else. And the same thing happens in solution. You have a high concentration and a low concentration, you put them together, eventually they're going to equalize. If you put some food coloring in water, at first you have a high concentration of those molecules right at the surface where you put it in, but then over time it distributes itself throughout the water. And if you just let that sit, even if you didn't mix it, just letting it sit for a long time, eventually it would all become homogeneous. So that's diffusion. It can apply to anything, solutes and things in solution. It can apply to gases in solution, whatever. So that's the most general term. And then osmosis and dialysis are specific about the movement of specific particles across a semi-permeable membrane. And so when we talk about osmosis, we're always talking about water. So it's about water moving through that barrier and going from areas of more water to areas of less water, which is areas of higher solute concentration. So if you have a higher solute concentration on one side of a membrane, the water is going to move toward where there's more solute, because we can also think of it as less water there. And that's osmosis. And then dialysis is generally focused on the non-water particles that are in solution. So the solutes moving through that membrane. It also can apply to water, but generally when we say dialysis, we're talking about solution and solution particles moving through a semipermeable membrane, because colloidal particles and suspended particles do not pass through that membrane. So in that example, you have a high solute concentration on one side, and the solute is moving the opposite direction through the membrane. We said this in the video, but I don't know if everybody caught it. This stuff is not going to be on this exam because there's a lab that kind of shows all of this and really helps with this definition. And we're going to do that lab in a couple of weeks after the exam and after Group B does their fat extraction lab. So we will hold off on this stuff, and this will not be on the exam. This will be on the final. All right, other questions? Okay, well, I'm not seeing anything. Format of the exam is the same as the last one. Yeah, it'll be just like the last one. If you have other questions and you want this format, you want me to talk more, I'm concerned that the Wednesday morning is just too close to the exam to really be of help, except that it's, for very last minute things. So if you want, send me some messages on Discord and we can do this again tomorrow night if you have more stuff that you want me to talk about. If it's something I can answer on Discord or an email or something, we can do that also. But yeah, let me know if you want me to do this again tomorrow night, even though that's not normally scheduled. But if you have questions, I'll come in and do that. Let's go over an unbalanced equation where you have to multiply by 2. Sure. All right, so that might be something like this one here. So what happens with these is you start to balance them like normal, and you go, okay, we've got C, H, and O, and on this side we've got 2 C's, 6 H's, and 2 O's, and on this side we've got 1 C, 2 H, and 1 O. So we start to balance. We know we're going to save the oxygen till last because this side has a bunch of oxygen. So that means that maybe we'll start with carbon. We can start with hydrogen too. It doesn't really matter. But we put a 2 here. That changes this from 1 to 2. It also changes our oxygen from 1. Whoops, that shouldn't have been 1 in the first place. That should have been 3. Changes that from 3 to 5. So now we're going to balance our hydrogen, and we've got 6 on the left and 2 on the right. So we need a 3 here so that we have 6 on the right. That changes our oxygen once more, and we have 7. So 4 plus 3 is 7. And here's where we get into that trouble, where there's no number that we can put here in front of the oxygen to make 7 total oxygen atoms, because we have to always multiply by 2, and you can't get 7 by multiplying by 2. So the solution then is to multiply everything else by 2 so that you turn an odd number into an even number. So if we put a 2 here and a 4 here and a 6 there, now we have 4, 12, 4, 12, and instead of 7, we should have 14. And the reason we double everything is just so that we don't have to balance everything again. We can just, all the work we did is still done. You could just say, well, let's go back and erase everything and just start with 2 of these. And that would also work. It's just a couple extra steps. But now we know we have 14 O's on the left and we need 14 on the right. So we can put a 7 here, and that gets us our 14 on the right. So that's where that sort of thing comes in. Whenever you're getting stuck like that, where there's just nothing you can do on one side to get to the number because of an even-odd situation, you multiply by 2 and you fix that situation. All right. Other questions? Good for now. Let me know if other things come up. Again, I can do this again tomorrow, or I can answer questions over Discord or email, or whatever is best for you. happy studying. And if I don't hear from you before, I'll see you all on Wednesday. Yes. Oh, I just saw another question. Can we do another unbalanced equation? Yes, but I don't have one off the top of my head. So let me pull one up here. All right, let's do this bottom one. Aluminum chloride, sodium hydroxide, then the products are aluminum hydroxide and sodium chloride. When you have polyatomic ions in an equation, sometimes it's helpful to keep those together. In this particular example, it doesn't matter all that much, but sometimes, like if you've got a lot of sulfates and phosphates and nitrates or whatever, if you have to count oxygens and all of those different things, it can be really confusing and potentially introduce errors. So it's easier to keep those ions together. So let's practice that here. In this equation, we've got on the left 1 aluminum, 3 chlorine, and 1 sodium. And then we're going to say we have 1 hydroxide because we know there's that polyatomic ion hydroxide and it's on both sides of the equation, which means it's not being split up or changing into anything else. So we can keep it together. On this side, 1 aluminum, 1 Cl, 1 Na, and 3 hydroxides. So the aluminums are good so far. Let's balance the chlorines. So we've got 1 here. We want that to be 3. So we're going to put a 3 there. And that's also going to change our sodium from 1 to 3. So now our sodium is no longer balanced. So to balance it again, we have to put a 3 there. That gives us 3 sodium. And that gives us 3 hydroxide, which actually helps us out because now the whole thing is balanced. So as I said, we kept the OH together. Here's an example of where that doesn't really work, where we've got phosphoric acid. You could think of this PO4 as a phosphate, but there's no PO4 on the other side. There's some other P's and O's doing other stuff. So that's clearly doing something in the reaction. It's not staying as a polyatomic ion throughout the reaction. So we would want to do this one as just H, P, and O on each side. And actually, let's do this one while we're looking at it. So we've got 2H, 2P, and 6O on the left. And then on the right, we've got 3H, 1P, sorry, P, and 4O. So with this one, again, like in the one a couple examples ago, we want to leave the oxygen till the end because the oxygens on the left are in multiple compounds. So we'll leave those to the end. It doesn't matter if we start with the H or the P in this case, or at least we don't think it does yet. So let's start with the P just because those numbers are nicer, because this one we've got 2 versus 3, and so we'd have to go like 3 and 2, which is fine, but P is easy, right? It's 2 here, 1 here. So we know if we just put a 2 there, we've got our 2 Ps. And then we can fix the rest of it. So we've got 6 H's now and 8 O's. All right. So now, again, we're going to keep the oxygens till the end. Let's jump over and look at the hydrogens. We've got 6 on the right, and we want to get 6 on the left. So we would put a 3 here. And that's going to give us 6 hydrogens, and then 3 plus 5 is 8 oxygens. And so now that's balanced. So that's it. Okay, well, I am going to say goodbye this time. But again, if you want me to do this more tomorrow, let me know. Otherwise, I'll see you Wednesday. Thanks, everybody.